Hello again. We're back looking at the electrodynamic ion traps experiment from Newtonian Labs. And what we've done now is we switched to the linear trap, and you can look at the documentation to see the geometry of the trap. Okay, and then the camera is looking down from the side, and I think it will become clear when we put some particles in, so let's do that. We'll just turn up the field and put a bunch of particles in. Okay, so there they are, lots of particles. And what's happening is the trap is a two-dimensional trap. It's linear, so there's trapping in two dimensions. So that's the vertical dimension as you see it, and the direction in and out of the screen. Okay, those are the main trapping direction. The left to right, there's very little trapping because it's a linear trap. We have these Teflon end caps that keep the particles centered to some degree, though. And here's the wand. I can put it in here. That's the wand. See, the wand will repel particles like so. It's great fun. You can push particles around using just the wand. So those are the electric fields from the wand. I charged the wand up, you see, and so it's negatively charged, and it will push those particles around. And so, as I like to say, you can literally poke a stick at these ion traps by sticking this wand in and seeing what it does. So there's my hand in the background. Those are my fingers. Okay, those are outside the trap. Okay. So I can turn the trap. Let me try to get that. Okay. So let's put some more particles in. So there we have that, and I'll just charge up my wand, stick it in there. And there's a bunch of particles, okay? So they repel each other, and so they don't fall to the center of the trap, the center being a line in this case, but instead they're spread out. So they're being pushed toward the center, toward a line in the center by the trap, and then the mutual repulsion keeps them apart. There's air currents that push them around a little because the trap is kind of open. And then finally there are the end caps that keep the particles centered in the trap. So there's a lot going on all at once. And again, if you look in the documentation, you can see the geometry, and that'll make it a little clearer. Now I have a DC voltage I can put on as well. It'll apply a static electric field, and so a static force. If I turn that down, then gravity pulls the particles down. If I turn it up, then the field will pull the particles up. Some of them will go away. And I can just tune it to the middle, and then basically gravity is being canceled. Okay, so I've got gravity pulling the particles down and the DC electric field pushing the particles up, and those two can cancel if I do it right. Okay, and so the particles will float in the center. But again, there's this Coulomb repulsion that keeps the cloud separate. So what I'm going to do now is I will turn the AC trap down, and it gets weaker. And the particles will start to leave because they get pulled up or pushed down from gravity, pulled from gravity and pulled up from the electric fields. And so I'll select particles. Okay, those with a lot of charge will get pulled up. Those with not very much charge will get pulled down. And in the middle, they all have fairly uniform charge, pretty much the same charge. So now if I turn this up a little bit, now you see they're all, whoops, getting a little bit of dust in there. There, that's not too bad. Now you see that they're pretty much on a line. Okay, so that's whoops, got a few more in there. There, that's what I had in mind. So that's a one-dimensional Coulomb crystal. So what you see, again, to recap, there's the trapping forces which push the particles toward the center of the trap. And the center, in this case, it's a two-dimensional trap, a linear trap. The center of the trap's a line. So the trapping forces, the AC trapping forces, push those particles toward the center line, the axis of the trap. They're the end caps that keep them from going left or right. Air currents push them around a little bit. You can see them just wobbling around. And there are DC currents, DC fields that will pull them up or down. Okay, and then gravity pushing them down. So I cancel gravity, and then of course finally there's the mutual repulsion of the particles. And so in the end, I have a Coulomb crystal, a one-dimensional Coulomb crystal, and you can make these however you like. You can make fewer. So there's a nice trap, 8 particles right in the trap. Okay, and they'll just sit there really indefinitely. If you block the openings, you reduce the air currents, and then they become quite stable, and they will just sit there. Okay, now I can turn up the fields higher, and you'll notice some of them go into these, whoops, I'm picking up some more particles, but some go into these, whoa, lots more particles. Okay, get rid of some of those. I was going to try to draw your attention to some of these extended orbits you see, like the one in the middle there. Okay, those are described in the documentation. There's an instability. If you turn the fields up too high, the orbits will become unstable and go into what we call extended orbits. And you can sort of, there's a nice line of atoms. And again, there's some of these orbits, these extended orbits. Okay, if I turn the AC down, the extended orbits go away, the trap becomes stable. Okay, if I turn it way down, I'll lose particles. Turn it back up again, they get more tightly confined, and then some of them go into these unstable orbits. And then sometimes I just pull particles right off the those bars. So you see some of the orbits here. Oops. Getting a little dirty in there, I think, so stuff just coming off from all over. Okay. Now here's a fun thing you can do, is we're going to turn this down and we just put in lots of particles here, a bunch of particles, and then we turn up the field and lo and behold they all pile into this clump of ions, and they're moving like crazy. They're actually rotating around in what we call a trapnado. Okay, and that's these extended orbits, and I describe it a little in the documentation. What's happening is you excite particles into these extended orbits, and they're moving round and round and round, orbiting around the center line, and that produces a bit of a fan effect. It blows air out, and when you blow air out, the sides, it pulls in from the center, and it actually, the air currents keep those ions connected together in this knot, and it will just sit there oscillating away, and you see occasionally particles can get sucked in. I'll put a few more in over here on the side, and you see them getting pulled up and just sucked into the trapnado. It is a little like a tornado in that it involves air currents. Okay, now if I turn it down, then it just goes back into a bunch of particles, and I turn it back up, and then I get 2 trapnados which combine into one. Okay. So I can play around just with the AC voltages and really make that thing dance in some crazy dances. And again, this happens all the time. Even if you're not looking for it, it will spontaneously happen. And so it's just an interesting phenomenon in these traps. And there we go. So that's some of the things you see when you are playing around with the linear trap. Okay, so let's try again. We can make a nice cluster. We can get rid of most of the particles and just have a nice stable line of particles. And we can turn it up and we'll get a few more coming in. We might get some of these extended orbits. There's one. Actually diamond shaped. It's a very nice view there. We'll push it around a little with the air currents, and you can see the diamond shape a little bit. Okay, crazy stuff. More diamond orbits, and then you turn it up and you get more and more, and pretty soon they all coalesce into a trapnado. Okay, that's enough of that. That's the linear trap. Thanks for listening. Hello again. What we're looking at here is a magnified view of the single particle trap, and there's not much to see right now because there are no particles in the trap, so let's turn up the voltage and we will drop some particles in using the wand, and there we have several particles. And what you're looking at here is what you'd see on the TV monitor. Okay, there's a built-in microscope on the single particle trap, and that gives you a pretty nice view, a magnified view of the center. And as you can see now, there are several particles in the trap. Each one appears as a streak. Okay, and this being a single particle trap, we would like to eliminate some of those particles and just look at one. So what we're going to do is we're going to turn the voltage on the trap down, and some of them, you see, the trap gets weaker, and some of the particles will go away, and we'll be left, hopefully, with one. Just turn it down and back up again until one of them is left. There we go, one particle left. The others have fallen out, and so it's a single particle. Okay, and as you can see, it goes nicely to the center, and that's because we have gravity balanced with a DC electric field. Okay, so the AC forces are pushing the particle to the center of the trap, and the DC voltage is balancing gravity. If I turn the DC voltage off, then you see the particle is pulled down by gravity, and it's pulled away from the trap center. And down at that position, the electric field, the AC electric field is non-zero, so it's a micromotion. If I turn the DC back up again, then I can set it at a point where I balance gravity. I can go beyond that as well. Now the DC fields are overcompensating for gravity, so the particle is pulled up. And if I do it just right, then I will compensate for gravity and have a particle nicely centered. So now the DC field, the forces from the DC field balance gravity, and so the particle is pushed to the center of the trap where there's no micromotion. Okay, so now I can use that to measure the charge to mass ratio, because right here the force of gravity, mg, is being balanced by the DC electric forces, QE. And I know E because I know the voltage applied to two plates, and I know the separation of those plates in the trap. Okay, and so I can calculate the electric field, and then mg is equal to QE, and I do the math, and I get the charge to mass ratio of that particle. So you saw how long that took. It's very, very fast. You just measure the voltage, do the calculation, you put a particle in, reduce it down to 1, and then balance gravity, and then you get Q over E. So you can do this multiple times with multiple particles if you want. Okay, so now we would like also to measure the mass of the particle so we can get the charge by itself. And the way we're going to do that is we're going to make a better image of the trap so we can measure the particle diameter. So right now the laser is shining on it, and the laser is very, very bright, so it just looks like a bright spot. We can get a better picture if we turn the laser off and turn an LED on. And so now you see the image is backlit. The particle is backlit with an LED. And so the particle is just sitting there, and we get a nice image of the particle. Again, if I change the DC fields, I can move it up and down. And you see that it gets blurry because there's micromotion up here. And there's micromotion down there, and so that gets blurred out. But if I get rid of the micromotion, then I just have a particle sitting nicely in the center of the trap. And if you look carefully, which you probably can't do because the video you're looking at doesn't have a high enough resolution, but this is an HD camera and an HD monitor, and I can see a pretty nice view of that particle, and it's not quite spherical. It has a characteristic corner on a sphere shape, these lycopodium particles, and you see that on the image. But they're roughly spherical, and one can measure the diameter of the particle just with a plastic ruler holding it up to the TV monitor. You can measure that and calibrate the image, and therefore get the diameter to about 10%, 20%. And so you measure the volume of that particle to maybe a factor of 2. And we know the density, and so therefore we measure the mass to a factor of 2. And from that we can use the charge to mass ratio and then get the charge out. And you'll find it's around 10 to the 5th electrons, typically. Okay, and so there you have it. You measure the charge to mass ratio, then measure the diameter. We know the density, and from that we can pull out the charge and mass independently. What's kind of fun about this experiment is quantitative. You can get real numbers, and when you go into it, what I like about it is you go into it, you have no idea what the charge on that particle is. I mean, none whatsoever. You just don't know, because you don't even know how to guess. And so here you started out with no idea how much charge there was, and now you know it to a factor of 2. That's something. And again, one can do multiple particles and get statistics and just play around with it. There's more we can do. Let's look again using the laser. Okay, here we go. If I turn the voltage up, okay, well, here's one thing I can do that's kind of fun. So I will balance this. I turn the trap down a little bit. So I'm looking at the DC again, and I will make sure it's nicely balanced. Now I'll just turn the trap off. Boom. Trap is off. There's no AC voltage anymore. And yet the particle just slowly drifts. And that's because there's just no force on it. Now I turned the AC back up to pull it in. But the DC voltage nicely balances gravity. So there's no gravity anymore. It's in a weightless environment. And the air currents are blocked because this trap is pretty well sealed up. There are a few holes for getting light in and particles in, but other than that, it's pretty sealed up. So unless I blow into it, there aren't too many air currents. And so, so everything's pretty well balanced. And so all I do is I turn the trap off right now, turning the trap off. The AC field is off, and the particle just slowly drifts out of the field of view until I turn the trap back on again. So that's kind of fun. Just you see that once you balance gravity, there's not too much else going on inside there. No other particles pushing around, and the stray fields are pretty small as well. So there's another thing I can do with this particle in the trap. It's sitting there stably, and if I turn the voltage up too high, it goes into one of these crazy unstable orbits. Okay, so I turn it back down, it's stable and nicely centered. I turn it up, and it goes into an extended orbit. Now what's going on there, we can look at this by strobing the laser. So I'm going to strobe the laser now. And there it goes. Okay, well, there's some little bit of artifacts from the strobing. But you see it going up and down, and it pauses a little as it crosses the center line when the fields go to 0. And if you want to understand that, well, it's a little subtle, but we have a little discussion of this in the Physics of the Ion Trapping document, and you can try to figure out what's going on. So what we're doing now is we're strobing the laser, so we're just seeing the motion of that particle. Now there's that bar going across the screen. That's an artifact of the camera running near 60 Hertz. But if you ignore that bar, then the particle is just going up and down in one of these extended orbits, and by strobing the laser, we're just seeing it in slow motion. So we stop the strobe, and there's the whole thing in the streak, and then we turn it on again, and we can see the motion. So one can really take data on this if you like. You turn it down, and it becomes stable again, and you turn it up, and it goes into an unstable, not quite unstable, but in an extended orbit. So it's just a phenomenon one can observe. Okay. So the main thing we like to do in this experiment is measure the charge to mass ratio of the particle, and then extract the mass, and really just characterize the particles. But just as an added benefit, we can then turn it up and look at this strange phenomenon of the extended orbits. At least at a qualitative level, we can have a little look and a little discussion of what's going on there as well. Okay, so there you have it, the single particle trap. One can do other things. You can measure, for example, the length of that streak as a function of the DC voltage applied. And from that, one can calculate the damping of the particle. And the damping is Stokes damping, and from that, you can extract the radius of the particle. And so that's another thing you can calculate. That's a little more advanced. But it's another way of getting at the radius of the particle in a dynamical way by looking at the damping from Stokes damping. Okay, so there's a lot you can do. The simple part is just measuring the charge to mass ratio and then the mass, and then it gets a little more advanced into looking at other aspects of the trap and of the particles. And so that's the single particle trap. We're just trying to make some quantitative measurements of the particles and the trap dynamics. Okay, that's all for that. Thanks for listening.
Photonics Laboratories has developed the laser source operating on new principles using semiconductor nanofabrication technology. The small chip in the center of the screen contains this laser source. Let's zoom in even further on the center section using an electron microscope. There are many holes arranged in a lattice in an indium phosphorus thin film that is only 0.2 micrometers thick. This is a photonic crystal. Here, embedded in a row with no holes, the laser source is constructed using 3 kinds of semiconductor compound. The hole lattice in the thin film changes the refractive index of the film significantly, preventing light from penetrating it and causing it to reflect. Thus, light can be confined to a narrow region by injecting it between lattices of these holes. We embedded an extremely small active layer having a length of 5 micrometers, a width of 0.3 micrometers, and a thickness of 0.15 micrometers. This large circle symbolizes the cross-section of a human hair, giving an impression of the small size of the active layer. The volume of the active layer is 1/10 that of earlier semiconductor lasers. We apply excitation light to the active layer. The active layer absorbs energy from the excitation light and begins to laze. The laser light jumps to a nearby waveguide and is output. Now we will test its operation. This confirms the ability to perform modulation at 20 gigabits per second. Despite its small size, it is able to perform high-speed modulation. Power consumption is at an extraordinary low level of 8.76 femtojoules per bit. At this speed, this is equivalent to transmitting data from more than 13 million DVDs using the energy of a single AA dry cell battery. Because of its small size and low power consumption, the photonic crystal laser is very promising for application in CPUs, for PCs, and servers. In current CPUs, nearly half of the power consumed is used for data transmission within the chip. Establishing data transmission layer integrating devices, such as photonic crystal lasers, would enable major decreases in power consumption. Our next subject is to control lasing using electrical current rather than excitation light. We expect photonic crystal lasers to become key devices for building optical networks within microprocessor chips.